So now let's consider an example. A 1 kilogram glider attached to the spring with the force constant equal to the 25 Newton per meter oscillates on the frictionless horizontal end track. At the time equal to 0, the glider is released from the lace at the x equal to the negative 3 centimeter. Okay, so we have the negative side of the x. It means that the spring is compressed by this length. So now for the part A, find the period of the glider's motion. Okay, so I think let's just list the variable that we know for the questions first. So we have the mass of the glider, right? So this is the variable m equal to the 1.00 kilogram. And we know the spring constant equal to the 25 Newton per meter. So this will be the K, the 25.0 Newton per meter. And then, okay, when the times equal to 0, the glider is released from x equal to the negative 3 centimeter. So we said that, okay, when the terms equal to the 0, x equal to the negative 3.00 centimeter, and it said that from rest, right? From rest. So it means that the initial velocity just equal to the 0. So then from this initial condition, we can say that the amplitude of the oscillation must be equal to the 3.00 centimeter as well, or just equal to the 3.00 times 10 to the negative 2 meter. So now for the part A, we just want to find the period of the glider motion. Okay, now for the part A. Okay, so we just want to find the period, right? But we know that the period is linked to the angular frequency. So we know that the omega equal to the 2 pi and then over the period 3, right? Equal to the square root of the spin constant K and then over the mass of the glider M. Then we can see that the period T equal to the 2 pi and then square root M over the K equal to, okay, so now let's just put in the number. We have the mass equal to the 1.00 kilogram and the spin constant, right, just the 25.0 Newton per meter. So then finally the period is equal to 1.26 seconds. Now for the part B. Find the maximum values of the speed and the acceleration. Okay, the maximum value of the speed and the acceleration. Okay, so let's see. We have equation already. The maximum value of the speed is equal to the omega times the A, and the maximum value of the acceleration equal to the omega square and then times the A, right? Okay, so we have, let's just start from the Vmax. Okay, the Vmax is equal to, actually because we're gonna use the omega, let me just plug in the number into this one to get the omega. So we have the square root of the 1.00, right, and then over the m, the K is 25.0 and the m is the 1.00. So then I got the number to be the 5.00 radian per second. So that's going to be the omega. Okay, so now for the Vmax, right, equal to the omega and then times the amplitude. The omega is just the 5.00, and now for the amplitude, right, equal to this value. Okay, so it's just equal to the 3.00 times 10 to the negative 2. So then the answer is 0.150 meter per second. Now for the Amax. Okay, for the Amax. From the equation, the Amax equal to the omega square and then times the amplitude A, right? The 5.00 square and then times the 3.00 times 10 to the negative 2. Then we get the 0.750 meter per second square. So these are answers for the part B. Now for the part C, okay, find the position, velocity, and the acceleration as a function of the times. Okay. Okay, so how about let's just start from the expression first. Let's just start from the expression first. Let's just start from the position first. So we said that from the from the position, right? From the x equal to a times the sine of the omega t plus the phi. Okay. So we said that when the terms equal to the 0, so the x here equal to the negative the 3.00 times 10 to the negative 2 meter, right? So this is what we know. So okay, if we plug in this into this equation, so we can solve for the phi here, right? Okay, so let's see. We have actually this one is equal to the negative a, right? So then we have negative a equal to the a, and then times the sine of the omega times the t, but t equal to the 0, so we have the 0 here, and then plus phi. Okay, then we have that the psi phi equal to negative 1. Okay, psi phi equal to negative 1. So then what is the phi? The psi phi equal to the negative 1, right? So it means that the phi here must be equal to the 270 degree, right? So you can just use calculator to check this number. Okay, so then finally we can get that the xt is equal to the 300 times 10 to the negative 2 meter, and then times the sine of the omega is what? Omega is 5 radian per second. So we have the 5.00 radian per second, and then times the t, and then plus 270 degree. So that's going to be the function of the x. So now for the v and the a, right? We can find the same thing. So we just can take derivative of the x to find the v. So now for the v, okay, the vt equal to the dx by dt, right? Then it's going to be equal to, okay, if we find the derivative of this function, right, it's going to be equal to the cosine function, and we must have the 5 radian per second multiplied with this one, which we know it already, equal to the 0.15 meter per second. Okay, then we have 0.150 meter per second, right? Just coming from the amplitude and then times the omega, so we can get the Vmax here, and then times the cosine of, so this will be the same thing, so we just write in this way. Okay, you just copy this into this term. Okay, Now for the A, right? Now for the A, okay? You can find derivative of the V respective to the T. That can be one thing. Or we can just use this relationship, the negative omega square and then times the X, right? So we have this relationship for the expression, negative omega square and then times the X. So I'm gonna try to plug in this X, okay, into these equations. So now you can see that this amplitude, right, just multiply with the omega square, which is equal to the A max, which is equal to the 0.750 meter per second square. Then in this case, we can get it to be negative 0.750 meter per second square, and then times the sine of this argument, okay, the same thing as this one. Okay, that's for the part C. So now for the part D, what is the total mechanical energy? What is the total mechanical energy? Let me move this to this position, then we can have some space. Okay, now for the part D, we need to find the total mechanical energy. So we have lots of the equations that we can use to solve, right? For example, okay, we can use 1/2 mv squared plus the 1/2 k x squared for any portion of the x, right, and for the specific v. Or we can just use the 1/2 m omega squared times a squared, or we can use the 1/2 k a squared. So in this case, I'm going to use this one because it will be the simplest one that we can see. Okay, so now for the E, right, it's just equal to the 1/2 times k and then times the a squared. K equal to what? K just equal to the 25 Newton per meter. Okay, we have the K, 25.0 Newton per meter. And now for the A, right, the amplitude, okay, it's just equal to the 3 times to the negative 2 meter. So we have the 3.00 times to the negative 2 meter and then square. Okay, then the answer is equal to 113, okay, times 10 to the negative 4 joules. Okay, another examples. An oscillator consists of the block attached to a spring. So we know the spring constant is equal to this K, right, the 400 Newton per meter. So we say that at some times T0, the position measured from the equilibrium velocity and the action of the block equal to this value. Okay, so this value is be the position, velocity, and the acceleration at this times T0 here. Calculate the frequency of the oscillations. Okay, so we just want to calculate the frequency of the oscillation. Okay, so how? Okay, let's see. If we just want to calculate the frequency of the oscillation, so let's say the omega, okay, you may think that, okay, if we look equation of the omega, so we have the omega equal to the square root k over m, right, or just equal to the 2 pi times the frequency, or the 2 pi over the period. Okay, but then if we use this equation, the omega equal to the square root k over m, we know the k. Okay, we know the k already. It's just equal to the 400 Newton per meter, but we don't know the mass of the oscillator, right? We don't know the mass of the oscillator, so it seems that we cannot use these equations, okay, because we don't know the mass. We just know only for the k, right? We don't know the mass. Okay, so how? what we know is we know the x, we know the v, and we know the a at this specific time, right? Actually, we have another equation that we can use to link between the a and the x, and then the omega. It is it is here, right? The a plus omega squared times the x equal to 0. Alright, okay? The a plus the omega squared times the x equal to 0. So then this question will work for any terms. Okay, then we can see that, okay, let me just use the a equal to the negative omega squared times x, right? Just be the same thing. Okay, so now let's just plug in this x and this expression. So we have the a equal to the negative 1, 2, 3 equal to negative of the omega square, and then times the x, right? 0.100. So then we can see that the omega is just equal to the square root of the 1, 2, 3 and over the 0.100, right, square root. Then the answer is 35.1 radian per second. Okay, now for the part B, we need to find the mass of the block. Okay, and that's it. So this is easy now, right? We can use the omega. We can use the omega equal to the square root of the k and then over the m. Okay, but now we need to find the mass, right? Or we can just rearrange to get that the m, okay, equal to the k and then over the omega square. Okay, so let's plug in the number. The k is the 400 and the omega is just the 35.1 n square. Then the mass of the oscillator, right, just equal to the 0.325 kilogram per c. The amplitude of the motions, okay, the amplitude of the motion. Okay, so let's see question that has the amplitudes first. Okay, we have this question, right? The E equal to, the E equal to the blah 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 here. Actually, we can use this question either because we said that the total mechanical energy of the system is constant, right? It means that if we, okay, we know the K, we know the X, and we know the v, right, for the times equal to t naught. Then we can find the e, and then okay, so this e, right, is just equal to this e, which is equal to the 1/2 m omega square a square. So it means that we can just solve for the amplitude a here. But now you can see that this technique is quite lengthy, I mean, it would say, right? Okay, actually I'm gonna use this one. Because we know the v and we know the x. Omega we also know, right? Then we can just solve for the a here. Okay, and that's it. So let's say that v equal to plus minus the omega square root of the a square minus the x square. Okay, we can move the omega to the left hand side and then square both sides of the equation. We have that the v square, let's say that the v over the omega square equal to the a square minus the x square, right? And then we can just rearrange equation to get for the amplitude a. we can see that the A equal to the V over the omega square plus the x square and then square root. So don't forget that when we just solve for the A, right, we can have the two roots. We can have the positive or negative root. But in this case, we know that the amplitude must always be positive, right? So that's why we just pick only the positive side here. And then, okay, so let's just plug in the number into the equations. So we have the square root of, okay, so now for the V, right, the V equal to the negative, the 13.6 meter per second, and then over the omega is just the 35.1 n square, okay, and then plus the x square. X is equal to 0.100 square, and then just take the square root. Okay, so then finally the amplitude is equal to the 0.400 meters